by itself, right? And as time goes on, the more that's learned, the more amazing your immune system is. So you guys, we're gonna do this so superficially, right? But hopefully, in getting the big picture, we can really appreciate how truly amazing your immune system is, because it is amazing. It's absolutely amazing. Okay, guys, so just to kind of give the big picture kind of concept map, you'll see on Canvas, you guys, there's two PowerPoints related to host defenses. The first PowerPoint, you guys, is what we'll start today. It's called Innate Non-Specific Defenses. And then the second PowerPoint that we'll probably won't get all the way through it next week, we'll just hit some highlights, is specific adaptive acquired immune responses. So let me just do a little concept map here to kind of put these PowerPoints in perspective. Oh, and also, folks, those of you in the 1 p.m. lab, I'll try to open lab around 12:30 or a little bit after. I have a 1 o'clock meeting I forgot about. But if you can, if you're in the 1 p.m. lab, you guys, if you can come in and start making your smears and gram staining early, that's the big bottleneck, is getting your gram stains in. So just so you know, you're welcome to come. Okay. All right. So historically, you guys, when we've talked about medical microbiology and infectious diseases, it was considered warfare. Like microbes were our enemies, right? So there's a lot of military, often a lot of military vocabulary that's used. So we talk about branches of the immune system, right? So if we think of our host defenses, immunity, you guys, it comes from the word for protection. We talk about 3 branches. Excuse me, let me back up. Let me do it a little bit simpler than that. We talk about 2 basic branches. And the first branch, you guys, is called non-specific innate defenses. Non-specific because these defenses provide protection against a wide range of microbes. Innate because these are defenses we're born with, and they're always ready to go. You know, they're very fast, very rapid. And there's 2 types, you guys, of non-specific innate defenses. So the first type are the surface non-specific defenses. And these defenses are provided by our skin and our mucous membrane. The first barriers that microbes encounter, you know, if they're trying to colonize us. And then the second type of non-specific defense, you guys, is if the microbe penetrates past our skin or our mucous membranes and it gets inside of us, luckily we have interior non-specific defenses. And just a couple of examples, you guys, we'll do more than this. Inflammation we'll describe. Phagocytosis, fever, and more. Okay. So again, you guys will, this is the first PowerPoint, we'll be describing surface and interior non-specific host defenses. Again, protects us against a wide range of microbes. It's always on, always ready to go. But sometimes, folks, those non-specific defenses, they aren't strong enough to protect us against an invading microbe, especially a microbe that has a lot of virulence factors. So the second branch, you guys, these are kind of like the big guns of our immune system. And this is what's called adaptive. In the past, it's been called specific, acquired, defenses or immunity. Specific because it will be active against a specific type of microbe. Adaptive because it's the system that lets us adapt to the pathogens in our surroundings. Acquired because we have to acquire memory of the pathogens and toxins that we meet in our environment. And here you guys, again, there's two types. There is humoral immunity. Humoral means fluids, and this is protection provided by antibodies, also known as immunoglobulins. And in general, folks, humoral immunity provides protection against extracellular pathogens and extracellular toxins. And then the second type, the second branch of adaptive specific acquired immunity, you guys, is called CMI, and that stands for cell-mediated immunity. And this is the branch that will protect us against intracellular pathogens. And an example, you guys, would be like viruses, right? Viruses are intracellular. They're replicating inside of our cells. Another function, you guys, of CMI that you will get into in A&P, we won't get into it in micro because we run out of time, is it also provides protection against cancer cells. And it's also responsible for transplant rejection. So transplanted cells, tissues, organs. But again, you guys, that's something I think they're gonna hit in A&P. We'll just focus on CMI, is it provides protection against intracellular pathogens. Okay. So folks, again, what we're first gonna do is we're gonna tackle the first lines of defense, the non-specific defenses. And we'll just start out, you guys, just kind of being, remember, we're being evolutionary biologists here. So we know from our lab experiments, the airborne place, you guys, did you see how many microbes are in the air? You know, you're breathing that in all the time, right? And way at the start of the course, you guys, we did some environmental sampling, you did some swabs and transferred the microbes to plates. So you saw that microbes were everywhere, right? So we could argue to you guys, if microbes are everywhere, why aren't we constantly infected, right? And so we want to remember that you guys are you guys represent survivors, right? We've been co-evolving with these microbes, and through natural selection, right, your ancestors were selected for their ability to withstand microbial invasion, right? So there were genetic variants in the human population, you know, a long time ago, as today. And so those humans that had the right genetic information to protect themselves against the microbes, they survived, they had offspring, and they passed those genes on. So we're so lucky, guys. We are the recipients of all those genes, right, that provide protection against microbes, right? And again, you guys, those layers of protection, the 3 different layers of protection, you'll have to forgive me, you guys, because by the end of the semester, I'm getting a little goofy and my imagination runs away with me. So I was trying to think, how can we make this more appealing, this whole idea of 3 layers of invention? And so you guys, I love Lord of the Rings. I was like, I know, it's just like Lord of the Rings. The attack on Helm's Deep. So we're going to use this as kind of our goofy example of the 3 lines of infection. So the pathogens, you guys, of course, were the orcs. The orcs were the pathogens trying to invade Helm's Deep. So this could represent our human. And so the first line of defense, you guys, were the outer walls. So that would be like our skin and mucous membranes. But those doggone orcs, they had a bomb and they blew up the outer wall. So they started to invade inside the fort. But within the fort, there were additional defenses. Maybe like people throwing rocks at the orcs, right? There were some more walls here that could provide protection. So the idea is, you guys, is if the outer defenses can't prevent infection, at least it slows down the pathogens, right? If they breach, if they penetrate the wall, there's still some interior non-specific defenses, which if they can't kill the pathogen, at least it slows them down until your hardcore warriors arrive, your adaptive specific acquired warriors, led by the T helper lymphocyte, Gandalf. I know you guys are such good sports to go along with this because I know you're all exhausted. Okay, but we're gonna attack it in those 3 levels, you guys. So some characteristics, you guys, of the non-specific innate defenses. Remember, they are fast. They're always ready to go. All eukaryotes have all eukaryotes have innate defenses. If we're lucky, innate defenses can actually kill the invaders right off the bat. We said that innate non-specific defenses will protect us against a wide range of microbes. They aren't tailored to specific antigens or specific microbes. But this is a disadvantage, you guys, of innate non-specific defenses. We don't develop what's called immunological memory. And immunological memory is the ability of our immune system to remember a pathogen. So if we are subsequently invaded by the same pathogen, we'll have a faster, stronger, longer lasting, more effective memory response or secondary immune response. Innate defenses don't have any memory. So with innate defenses, you guys, you get the same response over and over and over again, no matter how many times we're invaded by a given pathogen. So again, folks, this is a lot. Some of these slides, you guys, I borrowed from a new microbiology book. And I think the one thing I don't like about them is that there's so much text, and I think the text is sometimes overwhelming. So you guys, I'll put up on the board kind of the key points that I want you to know for the 5-1-TAM, okay? So as we said, you guys, we have these surface defenses. Our surface defenses, again, so we talked about skin and mucous membranes. So this is non-specific surface. So we have the physical barriers of the kind of like the walls of our port, right? And then, folks, in addition, we're going to have mechanical defenses, and this is the washing or flushing effect. To physically remove invading microbes. So for you guys, why is crying helpful? Yeah, because let's say you got like some dirt in your eye, right? And hopefully you start tearing, you start crying, and that physically can help wash out the invading microbes. In our intestines, you guys, the peristalsis, the movement of fluid and food and water, any microbe in the intestine that's not attached is going to get pooped out, right? So, or you could argue diarrhea is a way to help flush, right? Help flush out microbes. When we urinate, you guys, that's really important. And it's really important when you have to urinate, go urinate, don't try to hold your bladder, because the flow of the urine is going to help wash out pathogens like fecal bacteria that might be trying to ascend your urethra, right? So we can physically, a lot of flushing activity. And then chemical defenses, you guys. So this is going to include lysozyme, which is present in sweat, for example. And lysozyme, you guys, hydrolyzes peptidoglycan, right? Breaks down the cell walls of bacteria to provide protection. And it's present, you guys, and to me it's always amazing where we find these things. So lysozyme, you guys, in our tears, in the mucus blanket on the mucous membranes, it's in saliva. It's very cool, you guys, it's in breast milk. I think that's really cool. And then another chemical defense, you guys, is the hydrochloric acid in the stomach. So this is part of our protection against pathogens that we would swallow. And so we know the hydrochloric acid, it causes denaturation of proteins. So we're hoping it will kill a lot of pathogens that we swallow. But you guys, we know, since there's fecal oral transmission, we know a lot of pathogens we swallow still make it through the stomach alive. And it's probably because in food, the food itself provides kind of these little protective forts that can prevent the stomach acid from destroying the pathogens, right? the antimicrobial peptides, you guys, we aren't going to cover. So this one, you guys, we aren't going to cover this one. I do believe probably in A&P they do go over antimicrobial peptides, but for us, you guys, we just want to remember lysozyme and hydrochloric acid in the study for right now. So just giving a little bit more detail, you guys. Again, we look at the skin, right? Oh, you guys, why is it that burn victims are at such high risk for infection? Yeah, I mean, this is like our most important barrier of all is our intact skin, right? So burn patients that are at high risk for infection, always worry about burn patients, right? So part of the skin, you guys, is like the walls of a fort, where the skin cells hopefully are tightly adherent to one another, so physically the microbes can't move past them. Healthy skin, you guys, it should be dry, because a lot of pathogens need water, so the drier the skin, you could argue, then the less likely pathogens will grow. And it tends to be on the acidic side, and acids will inhibit the growth of some pathogens. This is really important, you guys, you're gonna see this over and over and over again. A really important part of our innate defenses is our microbiome. For if we have good non-disease causing microbes attached to our cells, that blocks attachment of potential pathogens. In addition, you guys, the good members of the microbiome, they'll compete for nutrients, and they'll also make potentially inhibitory metabolic waste products like acids. So we always forget, you guys, our microbiome is part of our natural defenses. We know that sweat, you guys, it has high sodium chloride, so it's supposed to be used for evaporative cooling. But the high salt will inhibit a lot of bacteria, and there's lysozyme present in the sweat. It's going to cleave the peptide glycan. The fatty acids that are present on the surface of the skin are antimicrobial. And the other cool thing, you guys, is the top layer of our skin, they're actually dead cells. They're chock full of a protein called keratin. And like every day, that top dead layer of cells, you guys, it gets sloughed off, means it falls off. And that is so cool, because you would predict, this is a cross section through skin, you guys. Here's this little layer up here. That's that layer of dead keratinized cells that we're going to slough off. You would predict that pathogens would bind to those dead cells, right? So if the dead cells just fall off, we're physically removing the pathogens. One trick that some pathogens have, for example, Staphylococcus aureus, one way that Staph aureus can get deeper into our tissues is that they can travel down these hair follicles. There should be a hair right here. So a lot of times Staph aureus will grow down into these hair follicles and then form a little abscess down at the bottom here. So Staph aureus are tricky in that they can get deeper into the skin and subcutaneous tissues without actually penetrating the skin. With mucous membranes, folks, mucous membranes tend to be much more delicate, right? Instead of having a layer of keratinized cells, they often have to be like really absorbent, like the mucosal cells of the intestine. But what they have instead is a sticky mucus blanket that acts as microbial flypaper, right? So the microbes get stuck in the mucus blanket, and then hopefully that mucus blanket will be moved out of the body, taking the pathogens with them. Mucous membranes, you guys, will also have the older cells will slough off and get moved out of the body, so if pathogens are attached, they'll get moved out. As we mentioned, you guys, especially in the intestinal tract, members of the normal microbiome are very protective against invading pathogens. There's lysozyme present in the mucus blanket. And this is a topic, you guys, that you've probably grown tired of. Another important part of natural defenses are ciliated cells of the upper respiratory tract and in the oviducts of women. So we just want to develop this a little bit more. This is probably a review from the first unit way back when we were talking about eukaryotic cells. So folks, if we talk about innate defenses of the upper respiratory tract, you'll recall that we said we have these beautiful ciliated cells in the upper respiratory tract that are constantly beating to move this mucus blanket right here, to move it up to the pharynx, right? So this mucus blanket, you guys, this is the sticky microbial flypaper. So if we inhale microbes, hopefully they'll get stuck here. And then your beautiful ciliated cells will beat to move the microbes in the mucus blanket in the back of the throat. And there we can either spit it out, right, physically remove the microbes, or if we swallow, right, hopefully the microbes will be killed in the low pH of the stomach. Yeah. So we had talked to you guys that of great concern is that if we have patients who maybe are chronic smokers, there's a lot of toxins in cigarette smoke, and they can damage these ciliated cells. So folks who have smoked for a long, long time, they're usually at higher risk for lower respiratory tract infections, right? Because their cilia can't move these trapped microbes out of the respiratory tract, and then the microbes can grow down and cause, say, pneumonia. Another concern, you guys, is when we have viral infections of these ciliated cells, like influenza, right? When the influenza viruses are replicating in the ciliated cells, that will harm them or decrease function. So following upper respiratory tract viral infections, very often people are at higher risk for secondary bacterial pneumonia. And again, it's for the same reason, you guys. If these little ciliated cells can't function, any inhaled microbes that get stuck in the mucus layer, they will not get moved back up to the throat, and instead they'll move down into the lower respiratory tract. Just some cool ciliated cells there, electron micrograph. And then folks, looking at surface defenses in the genital tract for both men and women. So again, you guys, in the genital tract of men and women, we have a nice sticky mucus blanket that will help trap microbes, and then the mucus blanket with the microbes will be moved out of the body, right? And we'll do the men first, you guys. In men, the flushing action of the urine is really important to keep invading pathogens out of the urethra. In women, the vaginal mucosa, it tends to be on the acidic side because of the good members of the microbiome, the lactic acid bacteria. They're fermenting, making lactic acids, and that's going to help inhibit a lot of opportunistic pathogens like Candida albicans. Yeah. Then let me see you guys. So, and again, this is kind of a repeat, you guys, from the start of the year. Another part of normal defenses in women is the ciliated cells in the fallopian tubes, or the oviducts. And the ciliated cells, they serve two functions. One is they're going to move the mucus blanket with any stuck pathogens to the uterus, and then they'll be expelled, right? So the ciliated cells are trying to move the mucus blanket with any stuck microbes, down and out. But another important function they serve, you guys, is when women ovulate, when they release an egg, the eggs don't have any flagella, any cilia. But the egg has to make this incredible journey up through the oviduct and fallopian tube into the uterus. So the second job of the ciliated cells is to create currents that will passively draw the egg up through the oviduct and then into the uterus. So a huge concern to you guys, and I know you've heard this talk before, but it kind of goes along with our concern with the increase in STIs, is in women who have chronic long-term infections, say with gonorrhea, Neisseria gonorrhea, and or chlamydia. And we want to remember, you guys, that Neisseria gonorrhea, it's a bacterium. And the agent that causes chlamydia is also a bacterium. So this is important, you guys. These infections, if caught early, can be successfully treated with antibiotics without there being any long-term damage. But the problem is, you guys, in women, what can happen, and just keep oriented, you guys. Here's the bladder and the urethra. Here's the vaginal canal and the uterus, and then here's the anus with the rectum here. The problem in women is that women can become infected in the genital tract without having the urethra colonized. And you're like, well, why is that a problem? It would actually be good news, you guys, if we always had the urethra colonized if we have a genital tract infection, because the inflammation will trigger burning sensation when you urinate. And you just kind of know, if you urinate and it's burning, something's wrong, I better go see the doctor, right? But what happens is some women, they'll have the genital tract infected without the urethra being infected. So when they urinate, everything's fine, right? And so with women, sometimes it's easier for women not to know they have a genital tract infection. And if they aren't receiving good medical care, right, at least getting a good checkup every year, they can have chronic, long-term Neisseria gonorrhea and chlamydia infections. So what? What's the problem, right? Well, those pathogens, you guys, they can cause ascending infections. They can move from the vagina through the cervix into the uterus, and then they can keep moving up, you guys. They can move into the oviducts, the fallopian tubes, and there they're going to trigger a really strong inflammatory response. And as a result, you guys, those beautiful ciliated cells can get damaged, right? So number one, that's going to decrease the woman's non-specific defenses, because now can't move that mucus blanket, right? Microbial fly fever out. But then second, if the woman ovulates, if she releases the egg, right? Maybe these ciliated cells are still working okay, but maybe these ciliated cells right here have been damaged. So the egg will get moved maybe partway through the oviduct, and then it's stuck, right? There's no more current, right? Because these ciliated cells are damaged. So the egg is stuck there. So then you might say, well, who cares, right? But what happens, folks, if the woman is inseminated, what do sperm have? Flagella, right? Have you seen those videos, how fast they swim, right? So they're racing, they're on a race to see who can find the egg first. And so they can swim right up into the oviducts. And when they meet the egg, they don't care where the egg is. You know, they're gonna fertilize, boom, right off the bat. But you guys, the problem is then, can that fertilized egg, can it move to the uterus where it needs to go to develop, right? It can't, it's stuck there in the wrong place. What do we call a pregnancy, you guys, in the wrong place? Yeah, so this is really serious, you guys. So we can end up with ectopic pregnancies, which can, you guys, be fatal for the mom, right? And the embryo's not going to make it. So that's a huge concern. And then, folks, we can get infection. We can get infection that act like this would be the peritoneal cavity out here. We can get an infection that spreads into the peritoneal cavity, and that can cause a really serious disease called PID, or pelvic inflammatory disease. And it can be so serious that a woman might need to be hospitalized with IV antibiotics. And another consequence, you guys, is if the inflammation, the infection goes on long enough, you can have permanent damage in the oviducts, like fibrosis here. And as a consequence, that might lead to infertility. Right? So, and this is all kind of heartbreak because, you know, like if the woman was getting those, you know, good medical checkup every year, and getting screened for these pathogens, and if it's found out that she is infected, you can take antibiotics, you guys, and boom, right off the bat, right? You get rid of the infection, and then you can stop any of these potentially serious sequelae, right? And furthermore, you guys, they've shown that women and men, you guys, that are infected with Neisseria gonorrhea and chlamydia, because of the inflammatory response, this draws a lot of white blood cells, a lot of leukocytes, and those are exactly the cells that WHO wants to invade. So another consequence, you guys, is if you have infections with Neisseria gonorrhea and chlamydia, it increases the risk of HIV infection. Right, because you're actually attracting the white blood cells that HIV wants to infect, right? So if you had maybe you were exposed to a low number of HIV, the more white blood cells that are hanging out there, the greater is the chance that one of those white blood cells is going to get infected, right? So that's another reason, you guys, you want to try to educate your patients that, you know, getting those yearly exams, and especially if they're sexually active, right? That it's really important to stay on top of the STIs, right? The bacteria we can treat, right? And by treating the bacterial pathogens, we can reduce their chance of maybe becoming infected with HIV. And of course, you guys, you want to talk to them about, you know, safe sex and what you can do to protect yourself, and yeah. Okay. And this, sorry you guys, I always do this on the board, but this is just, again, just repeating in text what we just covered. And folks, just because of time, I'm gonna skip these two topics on non-specific defenses of digestive tract and urinary tract. And again, you guys, I just say, you're gonna do a lot better job in A&P on this. So we're just gonna move on, you guys, to interior non-specific defenses. So you guys, we're gonna presume that the bacteria somehow, the pathogens somehow, they crossed the skin barrier, or they crossed the mucous membrane barrier. And this could be literally from an accident, some kind of penetrating injury. Like in this slide, you guys, they have the typical little wood sliver or sticker that's pierced the skin, introducing bacteria into deeper tissues. But you guys, it could also be like surgery, right? Surgery where intentionally cutting open the skin or mucous membrane. And that's a great way for pathogens to gain entry. It could be, you guys, through an animal bite, or it could be through the bite of a blood-feeding arthropod vector, right? So, unfortunately, there's a number of ways where pathogens can cross the outer surface defenses. So the question then is, you guys, well, then are we goners, right? Luckily, we have those interior non-specific defenses, and the few we're going to discuss, you guys, inflammation. These are a little bit outer. We'll do inflammation, phagocytosis, fever, complement activation, and interference. We probably won't finish today, you guys, but we'll get finished with this on Tuesday. So folks, inflammation is where we're going to start, and the follow-up slide, you guys, has a lot of information. So again, I just kind of want to put key points up here on the board. So we've done the surface defenses, and now we're working on our interior defenses, and we're first going to do inflammation. So we're first going to do inflammation. So inflammation, folks, this is our body's response to any kind of damage. It doesn't have to be microbial invasion. And indeed, you guys, I can trigger an inflammatory response just by causing tissue damage here on my arm. I'll just use my fingernail, and I'm doing mechanical damage to my cells here. So you guys, be careful when you do this, because sometimes you get carried away and you can really hurt yourself. So I'm doing some mechanical damage to my cells, and this is a really simplified explanation, you guys, but now my cells are releasing chemical messengers, and we're simply going to call it inflammatory mediators. Chemicals that are going to trigger the changes we associate with inflammation. And I know it might be kind of hard to see here, you guys, but I can see up close it's starting to get red, right? Starting to get red. I've met physical therapists that are so sensitive they can feel that an area that's inflamed is actually warmer to the touch than surrounding areas. So we have redness, we have heat, an increase in temperature. Eventually, you guys, this is going to get a little bit swollen, right? So we'll have swelling. And I can tell you already it's starting to hurt. So these are some of the cardinal signs, folks, of like the classic signs of inflammation. So we get the redness, right? We get heat, we get swelling, and we get pain. All right, so we want to understand, why is this happening? Why is this happening? So you guys, what I'll do is I'll put it up on the board kind of in steps, and we'll kind of flip back and forth to the PowerPoint slide, right? And also, you guys, I wanted to let you know that a lot of these key points are on the study guide / supplemental notes that we passed out. Okay, so this might be helpful for you. Okay, so you guys, so we're going to start out with our tissue damage, microbial invasion, And this then is gonna trigger the release, triggers the release of chemical messengers that we're gonna call inflammatory mediators. Or one of your colleagues yesterday, you guys, she made a good point, and she said, could these also be called cytokines? Oops.
It's okay. We'll punch in here, okay? Okay.
And the classic one, you guys, that most folks are probably familiar with is histamine. Okay, histamine? One of the chemical messengers that will help trigger some of the changes we associate with inflammation. Okay? So in response, you guys, to these chemical messengers, these inflammatory mediators, we're going to see some changes. And this is going to sound so familiar to you. So we're going to get some changes. So what are some of the changes? We're going to get vasodilation. Our vessels will become leaky. We're going to start leaking the fluid portion of the blood, the plasma portion, from inside the blood vessel to the outside. We're going to get leaky vessels. Okay. So you guys, with vasodilation, okay, so if this is the normal diameter of our vessel, vasodilation means the diameter gets bigger. That's going to permit more blood to flow, right? So vasodilation, that means locally, right, we're talking about local, we're going to get increased blood flow. And I'm going to put locally here, you guys, because we're going to compare this when we have like systemic wide inflammation. Okay, so locally. So you guys, the increased blood flow, what color is blood? It's red, right? So it's the increased blood flow that already is contributing to that redness. Okay, so the blood flow then is going to cause the redness. And folks, what's the temperature of blood? Compared to the outside air? It's warm, right? So the increased blood flow is responsible for what other sign? Heat, yeah. Heat. Okay. And then folks, if my vessels are getting leaky, right, and fluid is moving from the blood vessel lumen into the surrounding tissue, the extravascular tissue, how will that appear? Swelling, right? Swelling or edema? Good. Okay. All right. So the redness and the heat are from the vasodilation. The swelling is from the leaky vessels. And it's my understanding, you guys, that some of the inflammatory mediators can directly bind to our pain receptors and trigger pain, right? Now, let's just tackle pain really quick, you guys. It's kind of almost a philosophical question. So we might ask, well, why did we evolve pain receptors, right? It's something really unpleasant. But you guys, like as biologists, we would argue pain is telling us something is wrong, something needs to be changed, right? Now I'm going to be silly, guys, but what if I jammed this ruler into my arm, right? Is it important that I have some response like, oh, that hurts, I need to remove that ruler in my arm? I mean, is that silly? It is silly, right? But is it true? It is true, right? And we actually know, you guys, the importance of pain. Like in people who develop leprosy, a lot of times they lose a sense of feeling, maybe in their fingers or their toes. They don't feel any pain. And they're really high risk for causing all kinds of damage to their fingers and their toes because there's no feeling, there's no pain, right? So pain actually can be good for us, knowing that something has to be changed, right? Okay, so there's the pain for you. So you guys, let's walk through some of the description on this slide that goes along with our description on the board. And we'll develop this a little bit more. Okay, so here you guys, again, with inflammation, we have damage here, mechanical damage. We have introduction of microbial pathogens here, right? And that's going to trigger release of what? Yeah, the inflammatory mediators, the cytokines, right? And as a result of the release of those inflammatory mediators, what's going to happen to our blood vessels? Two changes. Vasodilation, right? So here's a longitudinal, you guys threw a blood vessel, right? So we're going to have vasodilation. That'll increase blood flow here. What else is gonna happen? They're gonna get leaky, yeah? And you guys, the little cells that make up the blood vessel walls are called endothelial cells. And what happens is, in response to the inflammatory mediator, they retract, they kind of pull inwards. And that's gonna increase the space between the endothelial cells. That's gonna be partly responsible for that leakage of fluid into the extravascular tissue, which will cause the swelling, right? Okay. Now, to this point, you guys are like, well, what's the advantage here? We could argue increased blood flow, it's gonna bring more red blood cells and oxygen, right? The increased blood flow, you guys, is gonna bring more white blood cells, leukocytes, cells of the immune system to the site of invasion, right? And we want them there to try to detect and destroy any invading pathogens. So you guys probably right now, in that area that I triggered inflammation, I might already have a type of white blood cell called a neutrophil patrolling that area, seeing if there's any invading microbes. If they find them, they try to attach to them, ingest them through phagocytosis and kill them, right? So I won't suffer a really serious infection. So another really cool thing, you guys, that happens in response to the inflammatory mediators is cells of the blood vessel walls express a molecule to which white blood cells or leukocytes can bind. And if we think of this, you guys, again, it's so elegant. Normally, white blood cells, they just be traveling, right, through the blood vessels. So we want them to leave the blood vessel and move towards the scene of invasion, like ground zero. So it's kind of like, well, how are you going to signal them? Well, by the cells of the blood vessel walls making a new molecule to which the white blood cells can bind, attached to, that's kind of signaling them, oh, we need to stop here and we need to squeeze our way between the blood vessel cell wall and go hunting for those pathogens, right? So you guys, if we could actually watch this, with a microscope, what would we notice in this area is the white blood cells are going to start to stick to the sides of the blood vessel walls, to the margins of the wall, right? And that process is called margination. Margination is when the white blood cells stick to the margins of the blood vessels, the walls, okay? So, and you guys, let's use as our example of the first responder are our neutrophils. They're the first to arrive on the scene of damage or infection. So we might call them newts for short. They're also known as PMNs. And that stands for polymorphonuclear leukocytes. And leukocytes are the white blood cells, the cells of our immune system. So PMNs, okay? And again, the neutrophils, their job is to arrive quickly at the scene of invasion and try to ingest, kill any invading pathogens by phagocytosis. So what we would see, you guys, like right now, we would see my neutrophils binding to the walls of the blood vessels, that process called margination. And then the coolest thing, you guys, they're going to squeeze between the endothelial cells, the cells of the blood vessel wall, and that process is called diapedesis. Please stick to walls of blood vessel. And then, you guys, after sticking to the wall of the blood vessel, they're going to squeeze between the endothelial cells, and that process is called diapedesis. So the neutrophils squeeze between the vessel endothelial cells. Because remember, they're hunting down the invader. They're hunting down the microbial invader. And then, folks, using concentration gradients of the inflammatory mediators, and if we have microbes in here, concentration gradient microbial products, in the process called what? what do we call movement along a chemical concentration gradient? Chemotaxis, right? So using chemotaxis, okay, the concentration gradient of inflammatory mediators and your microbial products, the newts move to site of injury and invasion. And then when they get there, you guys, if there's microbes that have been introduced, what's the job of the neutrophils? What are they gonna do? Yeah, phagocytosis. If they can, they'll attach to the invading microbe, bring it inside the cell, and destroy the microbe in the process called phagocytosis, right? So that process, you guys, is so important. It's probably going on all the time. We probably have little tiny sites of inflammation going on all the time. And then the newts, so in the process of phagocytosis, the newts kill invading microbes if they can, right? And again, you guys, this is probably going on all the time. You know, we have little breaches of our skin or mucous membranes, but because we get a fast, strong inflammatory response, and the neutrophils arrive, they gobble up any invading microbes, and we might not even know we had a little tiny infection at one time. And so this is pretty important. So again, folks, just to finish this. So we said the blood vessels dilate, become leaky, and express receptors for leukocytes, right? Then the circulating leukocytes, including our phagocytes, like the neutrophils, bind to the new receptors. That's called margination. And they squeeze between the endothelial cells. That's called diapedesis. They use chemotaxis to guide them to ground zero, right, where the damage, the invasion is. And then they'll try to kill any invading pathogens using phagocytosis, right? So you guys, you know, we can say we always, again, as evolutionary biologists, we always want to know, well, why? What's the advantage, right? So a couple of advantages, you guys, of inflammation is we're going to increase delivery of blood to the scene of damage and invasion. So that's going to increase oxygen delivery. It's going to increase delivery of white blood cells. And later, you guys will see, it will also increase delivery of antimicrobial products, such as complement, which we'll discuss, such as antibodies, right? And furthermore, you guys, inflammation, it's going to help attract the white blood cells, the leukocytes, and it's going to help activate them. And we'll talk about activation of leukocytes later. Okay, so this is really powerful. And it's, again, you guys, it's like boom, right? I had that little inflammatory response probably within a minute, right? So really fast. Yeah. Okay. And again, you guys, this was a slide that I borrowed from a new microbiology textbook. And again, it's a little bit overwhelming. So again, folks, what I want to say that if you know the key points up here and the key points on the study guide supplemental notes, that will do you fine on our final lecture exam, okay? Oh, I know one thing I did like about this, you guys, is it actually gives you names of more of the inflammatory mediators. There's whole tables of inflammatory mediators. And you guys, I will not ask you for any specific names, but those of you that have had AMP or will have AMP, I think they go into these in more detail. So they include histamine, probably the most famous one. There's kinins like eicosanoids, prostaglandins, leukotrienes, rhomboxanes. And I think, you guys, a lot of the anti-inflammatory drugs, they're targeting synthesis of some of these inflammatory mediators, right? And we did, you guys, talk about the increased blood flow. We talked about the vasodilation contributing to the redness and the heat, and the leaky vessels contributing to the swelling, and of course the pain receptors telling us, pay attention, we need to change something here. Now, folks, okay, the only thing, okay, well, actually, let me back up here. So, okay, we talked about how the inflammatory mediators, they're going to help attract the white blood cells and help guide them chemotaxis. We talked about the margination, you guys, of the diabetes. We talked about chemotaxis and phagocytosis. Okay. And we said, you guys, the first responders would be our neutrophils, and then, because we're gonna talk about macrophages here in just a moment. Another what we call professional phagocyte is a macrophage. It literally means big eater. And some authors describe them as the garbage trucks of the cell. And garbage trucks are so important, you guys. We would be overrun with garbage, right, if we didn't have garbage trucks. So it's not a description of low respect or disrespect for them. And indeed, you guys, macrophages have many advantages, okay? Neutrophils are very short-lived, maybe a couple of days. Macrophages can live a long time. They're slower than neutrophils, but they get there eventually. They're going to be longer lived, and very important, you guys, the macrophages are going to help trigger those specific adaptive immune responses. They're the bridge, one of the bridge cells between non-specific defenses and specific adaptive defenses. So they're really quite important. This part, you guys, don't worry about this. We're not going to get into resolution. Oh, but one thing, you guys, just out of, kind of tying things together, remember how we talked about pyogenic bacteria, pus producers, right? So pus may be a product of inflammation, especially if we have pyogenic bacteria that are secreting leukocytes that can kill all the white blood cells that are attracted to the scene of invasion. This slide, you guys, I know it's not very exciting, but this is truly, truly important, you guys. What does chronic mean? Long-term, right? And you guys, we're really appreciating how a lot of very serious diseases are caused from chronic inflammation, right? So again, you guys, this is an example of the double-edged sword of the immune system, right? We have to have it, right? Because we need it as a defense to kill invading microbes. But can it also harm us? It can, you guys. And we're going to see a lot of diseases have links to an immune response. And just to give you an idea, folks, so cardiovascular disease, atherosclerosis might be the product of chronic inflammation. Some cancers might be the product of chronic inflammation. And I'm thinking, you guys, like hepatitis B. If I get chronically infected with hepatitis B, some of the inflammation can, on top of the liver cells having to keep reproducing, replicating over and over, that might contribute to the increased risk for liver cancer. This one, you guys, is so, we always have like an epidemic of neurodegenerative diseases in our populations. So it's thought that chronic inflammation may play an important role in neurodegenerative diseases like multiple sclerosis and Alzheimer's disease, right? So this is really a really important area of research, is understanding the connection between chronic inflammation and these really serious diseases, and see if there's a way where we can kind of calm down the inflammatory response. Like sometimes it's just not appropriate. Yeah. And you guys, I didn't want you to panic on this slide, but it was just to remind me. Remember, you guys, how I said we want these changes to occur locally, right, where the infection has occurred, right? Do we want vasodilation and leaky vessels throughout our body? No, why not? It could kill us, right? Because if you have vasodilation, leaky vessels everywhere, your blood pressure goes down, you have decreased delivery of blood to your organs, and you can die from it, right? So we could say, you guys, that sepsis, and we talk about endotoxic shock, sepsis caused by gram-negative bacteria, say growing in your bloodstream or growing in your peritoneal cavity, that massive release of endotoxin, it triggers an inappropriate systemic-wide inflammatory response. So again, you guys, we want to have a good feel for the immune system, how it's absolutely essential, but the immune system can actually also harm us too, right? It has to be appropriate and ideally local, right? And without massive release of the inflammatory mediators, the cytokines. Yeah. Okay. So folks, let me just ask you, any questions just in general on the inflammation we went over? I know this is a lot of stuff, you guys, at the very end here. But again, you guys, I think maybe the study guide / notes, this will help having some of the key points in black and white. Okay, So you guys, what we're gonna do then is now we're gonna focus on phagocytosis, right? Okay. And the two phagocytes, you guys, that we're gonna use as kind of our model phagocytic cells. So we have inflammation. So we're still non-specific anterior, you guys. Now we're gonna have phagocytosis. And we can say cell eating. So cyto from cell, phago for eating. And the example, you guys, that we're going to use of what we call professional phagocytes, like this is one of their primary jobs, is to go around ingesting things. So you remember, you guys, the first responder is the neutrophil. And then slower to arrive, but very important, is the macrophage, right? So both cells play a really important role in trying to ingest invading pathogens. And so, folks, one thing that's, just an incredible question to ask is, well, how do our phagocytes know which cells to ingest, right? How do they know that they should be destroying microbes and not maybe destroying our own cells? So this has led to this really exciting area of research, you guys, into the receptors on our white blood cells. The receptors on our white blood cells that recognize unique microbial substances, substances our cells don't make. So we'll just do a little bit on this. Okay, so we'll talk about. So the question we can ask you guys in general, and it applies to our phagocytic cells, is how do leukocytes in general recognize microbial invaders? Like, how would a neutrophil know to bind to an invading bacterium? How would a macrophage know to bind to an invading bacterium? So it turns out the leukocytes have surface receptors for unique microbial substances. So meaning substances, you guys, our cells don't make. So we'll just use this PowerPoint cartoon, you guys, to help us out a little bit. So this would represent the surface, say, of a white blood cell, maybe of a phagocytic cell. And these are these unique receptors, you guys. And one group of these unique receptors, so they're called toll-like receptors. And it's kind of a funny story. So my understanding is there were some German scientists actually working with fruit flies, of all things, and perhaps doing some work with mutations, whatever. And my understanding is they came up with this really cool looking fruit fly mutant. And I think, you guys, in German, like where I would say cool, because I'm kind of old, it's like, oh, cool, that's so neat, right? In German, you'd say, toll, that's wild, man, that's crazy, yeah? And so they use this expression toll with this unique fruit fly mutant. And through several layers here, it was discovered these mutations related to these unique receptors, right? And so in honor of the German researchers, they were called toll-like receptors, TLRs. Just a little bit of background here, guys. But the reason, you guys, I wanted to show you this slide is I liked it because it showed, we can see the toll-like receptors, they have different numbers. So different toll-like receptors will bind to different unique microbial substances. And folks, you don't have to remember, like, oh, TLR4 binds to LPS. You guys, is LPS unique to some group of microbes? Who makes LPS? Gram-negative bacteria. So LPS is kind of a signal to cells of the immune system, we're being invaded by gram-negative bacteria. We need to mount an immune response, right? Where would we find flagellin? Flagellin is the protein that makes up bacterial flagella, right? So there's toll-like receptors that will recognize bacterial flagella, and that will be the alert, oh, we're being invaded. Here, folks, they have, and I like how they did this. So this group of toll-like receptors will recognize different components of microbial membranes and cell walls. What's a unique component, you guys, that gram-positive and gram-negative bacteria have in their cell walls? Something we don't make. I heard it. Peptidoglycan, right? So would it make sense, you guys? We might have toll-like receptors that would bind to peptidoglycan. We don't make it, right? The signal of being invaded. And there's toll-like receptors, you guys, that can even recognize unique fungal components. Yeah? So this is just a really cool, exciting, it still remains a really exciting area of research. And it's found out, you guys, that in some people that maybe suffer recurring infections, what they've discovered is that some people, their toll-like receptors might be, oh my God, the word just escaped me, non-functional. Like maybe a toll-like receptor, you guys, for example, isn't functioning, maybe it's mutant, so it can't recognize like fungal invaders. So that person might have recurrent problems, maybe with candida infections or fungal infections. So it's helping us understand why some people might be at higher risk for infections compared to others. Maybe their toll-like receptors are mutant, right? They just don't work well. Okay. All right, so then you guys, what we're gonna do is we're just gonna walk through the steps in phagocytosis. And this is a really amazing process, you guys, absolutely amazing process. So folks, how would the phagocytes find the scenes of microbial invasion? What's the process? Chemotaxis, right? So that's how the phagocytes, say the neutrophils and macrophages, are gonna find the microbial invaders. Good. And then, you guys, it's important that the phagocytes have some surface receptor that can bind to some molecule on the surface of the microbe, right? Because they have to be able to attach to an invading microbe. Now, here's a question, you guys probably remember this from the last lecture exam. Do our phagocytes have receptors for capsular polysaccharides? No, they don't. And what's the consequence? Vanessa, will you be my encapsulated bacterium and I'll be the phagocyte? You just have to sit here. So Vanessa's my encapsulated bacterium. I'm the phagocyte, right? Vanessa's covered in capsular polysaccharide. Is there anything I can attach to? No, there's nothing. And so even though I might try to attach, there's nothing to attach to, and the encapsulated bacteria escapes. So that's why we say the capsules are anti-phagocytic, right? Our phagocytes lack receptors to bind to them. Pretty sneaky, right? Okay. All right, so hopefully our phagocytes will have receptors to bind to some unique molecule on the surface of the microbe. And so then you guys will see either the pseudopods forming and fusing, or we might have an invagination of the cell membrane. So eventually the pathogen is brought into the inside of the phagocyte in this membrane-bound vesicle called a phagosome. Phago means eating, some means body, right? But you guys, this is how should I say this? We're not out of danger yet, because some microbes have learned to happily replicate inside the phagosomes. It's kind of a nice place to be, right? So obviously we have to have some more specific killing mechanisms. So you guys, there's two different ways that phagocytes are going to try to kill that invading microbe. And I like to think of it, you guys, as a 1-2 blow. So Vanessa, I don't need to be beating up on you, but let's say that Vanessa is my invading pathogen. So I'm like, pow, oh, she's tough, man, that didn't do it. So now, pow, 1-2 blow to make sure that I can kill that invading pathogen. So you guys, the two processes are called oxygen-independent killing and oxygen-dependent killing. So let's talk about them. Here's our phagosome with our ingested microbial pathogen. The next important step, you guys, for killing is that another membrane-bound organelle, the lysosome, the lysine body, a membrane-bound vesicle chock-filled with hydrolytic enzymes, digestive enzymes, is going to fuse with the phagosome. to form, and again, this is like in German, where you just keep adding words together, to form the phagolysosome. This is where the microbe will be killed, right? So you guys, really fascinating. These hydrolytic enzymes, these digestive enzymes, they're acid activated, right? They're in the wrong shape until the pH is lowered, and then they're gonna change shape, and then they become active, right? So to activate those hydrolytic enzymes, you guys, there's proton pumps. There's proton pumps in the membrane of the phagolysosome that are pumping protons into the phagolysosome to acidify it. Without acidification, these hydrolytic enzymes, these digestive enzymes, will be non-functional, right? Well, some microbes have figured out how to block the proton pumps. So without acidification, those digestive enzymes will never harm them. Isn't that sneaky? It's just brilliant, the strategies they've evolved. Okay, but you guys, let's say this is normal. So we have proton pumping, acidification of the phagolysosome, the digestive enzymes, the hydrolytic enzymes are activated. We'll have like proteases and nucleases, maybe lipases to help tear apart the microbe. But some of the microbes, you guys, you know, they might, maybe because they have a really maybe acid-fast cell wall, right? Maybe they can resist those hydrolytic enzymes. So the second punch, you guys, the second killing mechanism is called oxygen dependent, because we see a huge increase in molecular oxygen consumption. It's sometimes referred to as the oxidative burst or respiratory burst. And in this oxygen dependent killing, you guys, there's enzyme systems in the membrane of the phagolysosome that take oxygen and help convert it into toxic reactive oxygen intermediates, like superoxide radical or anion, like hydrogen peroxide, right? So those toxic superoxide anions, hydrogen peroxide, even a bleach-like substance, you guys, that's the second blow to try to make sure that microbe is killed, right? So you guys, if I ask you on the exam, what do we mean by oxygen-independent killing? Can you describe what oxygen-independent killing is? Those acid-activated hydrolytic enzymes, the digestive enzymes. How do we acidify the phagolysosome? We pump protons in, right, from the cytoplasm into the phagolysosome. Good job, you guys. What do I mean by oxygen-dependent killing? How would you describe that? Production of those toxic reactive oxygen intermediates such as superoxide radical, hydrogen peroxide, even bleach-like substances, right? Yeah, okay. So you guys, so with a 1-2 punch, hopefully we kill the microbe, the little is digested, we'll absorb some nutrients, and then we have a waste vesicle. And folks, the waste vesicle will migrate to the cytoplasmic membrane and fuse, and through the process of exocytosis, dump all that garbage to the outside.
Is that the job of the macrophage?
Pardon?
Is that the job of the macrophage?
Macrophages and neutrophils both can do this, the professional phagocytes, yeah. But you guys, this is actually a problem. Remember how we said there's a lot of problems with chronic inflammation? Like think of Mycobacterium tuberculosis, you guys, in our lungs. It has that nice acid-fast cell wall. Sometimes our phagocytes, our immune system, our immune response will not kill the mycobacterium, right? So we end up with chronic infection, maybe chronic inflammation. So one of the problems, you guys, with chronic infection, chronic inflammation, you continue to attract phagocytic cells, right? And they're trying to do their job, but maybe they can't quite get it done. And one of the problems is, you guys, phagocytic cells, one day they're gonna die. And when they die, they're gonna release all those hydrolytic enzymes. You know, potentially they'll release those toxic reactive oxygen intermediates. And another problem, you guys, I'm laughing, I shouldn't laugh. But one author was talking about how in some phagocytes, they get a little bit confused. And what happens is that lysosomes will actually fuse with the cytoplasmic membrane and dump those hydrolytic enzymes to the outside. If you've had chronic inflammation, right? You might have an area that does have a low pH, and you end up activating those enzymes, and they start attacking your own cells, right? So such phagocytes are called sloppy feeders, right? So you guys, we want to recognize that, you know, again, we have to have our phagocytes, But in chronic inflammation, chronic infections, and phagocytes can actually contribute to a lot of tissue damage. Okay, so you guys, on that happy note, okay, so you guys, half of you have a great weekend, and then the other half of you guys will try to get down to the lab at 12:30 to open it, so you can start